Okay, we're going to review question 9 from your quiz on infinite limits and continuity, because a lot of you struggled with using the three-part definition of continuity. So let's take a look at this. I'm going to work through each of these, so let's just start on part A. We want to verify that f of x is continuous at x equals 5. So first of all, I told you that it should be continuous, so I'm not actually asking. I could have, but I was trying to help you out a little bit here. So first part is we need to figure out, is the functional value defined at x equals whatever number? So is f of a defined in this case? We're looking at f of 5. So rather than just saying it's defined, we're going to have to know in part 3 ultimately what it is. So I'm just going to go ahead and say what f of 5 is. So I'm looking up here and I've got a 5 and I've got a 5. So the first thing that I'm noting is I'm not using this first piece of my piecewise function at all, because that's only concerned with x is less than 2 and I'm well beyond 2. So now I'm going to look where it's the equal part, and obviously we've got the equal part right here. So when x is equal to 5, my function is f of x equals negative 3. That's a horizontal line, y equals negative 3. The value is always negative 3. So f of 5 is in fact negative 3. That's part 1. Part 2 for my definition of continuity, or condition 2 if you want to think of it that way, is I need to figure out what is the limit as x approaches 5 of my function. And this one's tricky. Here's where some of us ran into trouble, because we got this confused with the third part and actually ended up doing part 2 over a couple parts. There's an implied step that you have to go through before you can actually answer this. So I'm going to ignore this for a second. And I'm going to come over here and I'm actually going to do a little bit of work on the side up here. And I'm going to figure out, we'll just work over here. I'm going to figure out two things. The first thing I'm going to do is the limit as x approaches 5 from the left of my function. And then I'm going to figure out the limit as x is approaching 5 from the right. Recall that the definition of a limit, or two-sided limit, is it's equal to both of the one-sided limits when they're equal to each other. If, in fact, the one-sided limits aren't equal to each other, I don't actually have a limit. So my left-hand limit is using this function here, because that's what function is defined, or what piece is defined from a piecewise function when x is approaching 5 but lower than 5. So that one's just negative 3, same as we got for the functional value. Not interesting, but I need to note that. So I'm hoping this other one comes out to negative 3. But if in fact I plug in a 5 into my x's here, I'm going to get 25 minus 13 times 5 is, I believe, 65, plus 40 over 5 minus 5 is 0, and that in fact gives me 0 over 0. So some of us stopped there, some of us got a combination of did some bad mental math and didn't get 0 over 0. Point is, that is an old problem. I shouldn't be afraid of this anymore. This 0 over 0 is not okay. But let's return to what we know about evaluating limits from earlier in this chapter. And I should be thinking something like factoring. So if I do go ahead and factor this one, I'm going to get x minus 8 and x minus 5 over x minus 5. That again is me factoring this function. X minus 5 factors cancel out. I'm down to limit as x approaches 5 from the right of my function. X minus 8 is my simplified function. So that's the same as the original function at every point except for when x is equal to 5. I don't care about when x is equal to 5, because limit only cares about what's happening around the point, not at the point. So for all practical purposes, for a limit problem, I can use my simplified function, which now allows me to just plug in my 5 and get 5 minus 8, which is negative 3. So that was a little bit of work. I'm now comparing my right-hand limit with my left-hand limit, and because those are equal, I can say at this point that my actual limit as I'm approaching 5, two-sided limit, is negative 3. Okay, graphically, that means that I'm approaching the same thing, so 5 is over here, and I'm approaching negative 3 from the left and negative 3 from the right, so I may have a hole in the graph, but I'm approaching the same thing. Part 3 of my definition of continuity, or condition 3, 2 is by far the longest part of it. When I get to part 3, I'm now looking at because again, that was all for part 2. Part 3 is my functional value equal to my limit as x approaches 5 of my function? And there's a question mark right now over that equals. So if I can say, in fact, they are equal, then I not only know that they're approaching the same thing, but it's actually defined at that point versus being defined above or below it at a different point. And in this case, it's just a simple compare your numbers. So I've got the limit is -3. I've got the functional value was this, -3. And are they equal to each other? In fact, they are. -3 is equal to -3. So at this point, I can say, therefore, f of x is continuous at x equals 5. And that is basically my proof, is this right here, me showing that the limit is equal to the functional value allows me to make this conclusion about therefore. But without parts 1 and 2, you really don't have enough to say. You have to show that in order to verify what we're saying in step 3. Okay, we're going to go through the same process with part B, which is just looking at x equals 2 is the function continuous. So here we go, same problem, but now we're going to look at part B. And in this case, I'm looking at x equals 2. So the first thing I'm going to do is I'm going to ignore this part of my function because I don't care about when x is equal to 5. I'm at x equals 2, and there's a 2, and there's a 2. So for the left hand, I'm going to look at the top piece, and the right hand, I'm going to look at the middle piece. So is the function continuous at x equals 2? I need to give myself a little more room. So look at your paper. So you've got the function in front of you. Step 1 is the function defined? At 2. So f of 2 is, and in this case I'm using the top piece, that's where the equal part is. So 2 minus 2 squared, which is 2 minus 4, which is -2. Second part, I'm doing the limit as x approaches 2 of my function. And before I can answer this, I'm going to do my one-sided limit. So I'm going to actually come over here, come up here and use this space. Ignoring this question, I'm just going to work out my one-sided limits. So in fact, my left-hand limit x approaches 2 from the left is using my top piece, 2 minus 2 squared, and in fact I already figured out that that's a -2. I don't have to do any algebra manipulation here. Our first process, or first step, first thing we try whenever we're trying to evaluate a limit is simply plug in the value. It worked this time. So moving on, limit as I'm approaching 2 from the right of my function. Now I'm using this piece here, the middle piece, because that's for when x is greater than 2 or 2 is less than x, saying the same thing, but if you like to think of it this way, that makes a little more sense to my brain. If I'm using that piece, then I get a -3. There's nothing to plug into. It's the limit of a constant. Limit of a constant is that constant. So I've got left-hand limit -2, right-hand limit -3, not equal to each other last time I checked. So different situation than we had before. When I get down to number 2 here, because I have unequal one-sided limits, I've got does not exist for my limit as x is approaching 2. So if we were to, in fact, go to step 3 and try to say, is f of 2 equal to the limit as x approaches 2 of my function? Again, that's a question mark. Well, it's an automatic no here because this one does not exist. So no matter what I got for the functional value, it's never going to be equal to a does not exist value. So we're pretty much okay at the end of step 2 to go ahead and make our conclusion that our function is discontinuous. So therefore is discontinuous. I'm abbreviating to fit it on the screen here. Discontinuous at x equals 2. Since the limit does not exist. And furthermore, I ask you to describe the point of discontinuity. So that would be me asking, is it a removable point of removable discontinuity or non-removable discontinuity? And I like to go back to the graphical look here. We just said that the limit does not exist. So how does a limit not exist? Well, we said up here the left hand and the right hand limits aren't equal to each other. So this is just me drawing a pathetic graph here because I have no idea what it's going to look like, but I know that I'm at x equals 2, and from the left I'm approaching negative 2. So I don't care if it's a line or what it is, but I'm approaching negative 2 from the left, so let's find negative 2 here. Here's negative 2 and there's negative 3, so from the left I'm approaching negative 2, and from the right I'm approaching negative 3. And no matter what's happening here, well, I am in fact defined at this point. But the point is that you're thinking, okay, you're not approaching the same thing from the left and the right. So that becomes when I have a jump discontinuity. I can't just change one of these values because I'd have to change an entire piece there. So limit does not exist. There's a jump discontinuity at x equals 2, or if you had said a non-removable discontinuity, I would have taken that as well. Okay, how would we get a removable point of discontinuity? That would be if, in fact, the functional value and the limit were both defined, so we had an answer to part 1 and 2, but they were not equal to each other. So going back to the one we did before, we had values for both. If we had gotten here and these weren't equal, then that means I have a limit, I'm approaching the same thing from both sides, but I don't actually have a point there. Hopefully that helps to clarify the idea of continuity and how I use that 3-part definition or the 3 conditions to verify whether a function is or is not continuous at a point.